Hi, so today we'll be talking about circuit reduction. Now, what exactly is circuit reduction? So circuit reduction is making a large circuit into a smaller one, and that basically allows you to make one big problem into many smaller ones. This allows you to do the calculations much easier, and it's a nice analysis technique. Now, before we start circuit reduction, there are two resistance laws that you should know, and the first one is if the resistors are in series, the equivalent resistance is the sum of the individual resistors. The second law is if there are resistors in parallel, the equivalent resistance is the reciprocal of the sum of the reciprocal of the resistances. Now the second law kind of sounds confusing, but I'll get to that soon to make sure you understand it properly. Now for the series law here, we can see there's a 30-volt source, and there will be a current that runs through the battery. As you can see, there are three resistances, R1, R2, R3, 5 ohms, 10 ohms, and 3 ohms. So this is the before circuit, and this is the after circuit. As you can see in the after circuit, there's only one resistor, where else in the before there are three. This is because we simplified the three resistors. Now, when current travels in one path, it's in series. So all these resistors right now are in series because there's only one path. You can only go here, 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 here. It's just one single path. So when resistors are in series, like I said before, you add the resistances. So step 1, add the individual resistances. RT is R total, so it's equal to R1 plus R2 plus R3, which is 5 plus 10 plus 3, which is 18 ohms, which is what we have here. So these two circuits are exactly identical, but this one is much easier to solve with than this one, and that's series law. And now for parallel law. Parallel. So as you can see, there's a 30-volt source, and if the current starts here, so we'll call it I1. So it travels. Once it reaches here, I1 can now go in two directions. It can either go down, it can either go down or it can go right. So as you can see, there's more than one path. So if you look at this circuit, the resistances are in parallel. There's one here, there's one here, there's one here, there's one here. Now let's look at step 1. So first you take the reciprocal of each resistor. So the reciprocal of 1 is 1, the reciprocal of 2 is 1 over 2, the reciprocal of 3 is 1 over 3, and the reciprocal of 4 is 1 over 4. So then step 2, you add them. So the formula is 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3, and 1, 2, 3. Oh, this should be a plus 1 over R4. Sorry about that. So it's 1 over R1 is the reciprocal of R1, 1 over R2 is the reciprocal of R2, 1 over R3 is the reciprocal of R3, and 1 over 4 is the reciprocal of R4. So if you take the reciprocal, you have 1 over 2, 1 over 3, 1 over 4. So you add them, obviously, so it's 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, which gives you 25 over 12. So 1 over RT equals 25 over 12. So if you take the reciprocal of 1 over RT, that's RT, so you have to take the reciprocal of this, and that's 12 over 25, and that's 0.48 ohms. So that is your equivalent resistance when you have resistances in parallel. So in series, you just simply add them. It would have been 1 plus 2 plus 3 plus 4. But in parallel, it doesn't work like that. You have to use this law. Now this circuit and this circuit are the exact same. But once again, it's much easier to do calculations with this one over this one. And note, the reciprocal of a number is 1 over the number. Now there's series and parallel. So this circuit has a combination. Some are in series and some are in parallel. So we're going to go over how you simplify the circuit. So as you can see, when you look at the circuit, you have a 20 ohm, a 10 ohm, a 5 ohm, and a 5 ohm. Now series is when there's only one path. So as you can see, if the current started here, it goes here. It can split off into two directions. It can go either down or it can go right. Now the current that goes right, there's only one path. You can only go here. So as you can see, these two resistances are in series. There's just one, it's just one path, they're not parallel. So you can add them. So 5 plus 5 would be 10. So that's how we get this 10 ohms. So all we did was we added these two and we simplified it to this. Now you have this circuit. So you've got this resistance, and you've got three resistances now, 20, 10, and 10. Now as you can see, these two resistances are in parallel. So now we can use the parallel law and simplify these two into one resistance. And that gives you R2. I simplified the math. It's, as I said before, you take the reciprocal of this, which is 1 over 10, reciprocal of this, which is 1 over 10. You add them, so 1 over 10 plus 1 over 10 is where you get this. And then you take the reciprocal of that, which is 1 divided by that. And this gives you 5 ohms. So these two resistances combined gives you 5 ohms. Now, you look at the circuit you have, and you realize, oh, 20 ohms, 5 ohms, and they're connected in series, so you just add them. And you get 25. This is the same circuit as this one, and once again, it's much easier to do calculations with this. Now, this is the math from the previous slide. Step 1 was adding the two series resistors, so it was 5 plus 5 equals 10. And step 2 to step 3 was adding the series in parallel. So I did the math here. 1 over R, it was equal to 1 over R1 plus 1 over R2. 1 over R1 is 1 over 10. 1 over R2 is 1 over 10. Add them, you get 1 over 5. And that's 1 over R equals 1 over 5. So you take the reciprocal, so R equals 5. And then step 3 to step 4, you just add the resistors in series. 20 plus 25 equals 25. Now, before we move on, we have to talk about current and voltage. So, resistances that are parallel with other resistances and a voltage source have the same voltage. Resistances that are in series have the same current. Now, the current that flows through, now I have some examples here, but the current that flows through R1 is the exact same as the current that flows through R2. So if there was a current entering here, the current that goes through here is the exact same as the current that goes through here in a straight line. And this they are both series. So the current that goes through here, obviously, it's just the path is still linear, still the same. It's one path. So they're both series. Now the voltage that is in R1 is the exact same as the voltage in R2, as you can see below. So here and here. The voltage in this circuit, in this resistance, is the exact same as the voltage in this. The voltage source and R3 also have the same voltage. By the way, there should be a line here, but so let's say this voltage source was 50 volts, then the voltage for this resistance is 50. And these are very useful when it comes to using circuit reduction to solve circuits. Now, a lot of people get confused on why voltage is the same in parallel. So let's talk about voltage. So what is voltage? Voltage is the difference of electric field potential between 2 points. Parallel resistors have the same 2 points. If a voltage source is connected to point 1 and point 2, then the voltage drop should be the same as the voltage source. So the voltage drop equals the voltage source. So let's look at that here. We have 100 volts. This is the voltage source. And we have two resistors in parallel, and they're also parallel to the voltage source. And as you can see, they all have the same point. Point 1 actually extends all here. Point 2 also extends all here. And so they have the exact same 2 points, and they're parallel, and so the voltage drop for this resistor and this resistor are both 100 volts. Now if they're resistors in series, then the voltage from each resistor is summed up to equal the voltage source. So as you can see, the voltage source is 100 volts here, and we have three resistors, V1, V2, V3. If we were to add the voltage of V1, V2, and V3, they should equal 100. But they could be the same, but that does not necessarily mean they will be the same. These voltages can be completely different, and they can be completely different, or they could be the same, but that depends on the calculations and the numbers you're given. But in parallel, they will always be the same. And in series, well, you add them up and they should equal 100. Now let's do some circuit questions. So question 1, we're going to solve for I1, I2, I3, and the voltage V1, V2, V3 using circuit reduction. Now we have a 80 volt voltage source, we have 3 resistances, a 10 ohm, a 20 ohm, and another 20 ohm. So if you look at the circuit and you look at the current, you can see I1 leaves the voltage source and it comes to this point, and it can go in two directions. It can go right and it can go down. We're going to call down I2 and we're going to call right I3. But as you can see, I1 is being split into two. So if, let's say there were 10 people walking, 10 people walk here, 10 people can go from here, they split paths. Here, they can go right or they can go left. Sorry, they can go right or they can go down. Let's say 8 people go down and 2 people go right. That's what it means. 10 people split into 8 and 2. 8 plus 2 is 10. So that's why I1 equals I2 plus I3. And you should remember this. Now, when we start circuit reduction, we can see that these two resistors are in series, the 20 ohm and the 20 ohm, so we can add them. So we've added them. 20 plus 20 equals 40. That's where we get 40. And if we look at the circuit remaining, we have a 10 ohm and a 40 ohm in parallel. So we add those, and we get 8 ohms. So we have simplified our original circuit into this simple, nice one, an 80 volt voltage source and an 8 ohm resistor. So now we'll start solving for the values we need, I1, I2, I3, and V1, V2, V3. So this is what we had. So we're going to solve for I1. This is simply using Ohm's law. So I1 equals V over R, which is 80 over 8, which is 10 amps. So then we're going to, when it comes to circuit reduction, you simplify the large circuit into the smaller one, then you slowly build back up to the bigger circuit. So as you can see, here we went from this step to this step to this step. Now we're going to go from this step to this step to this step. So we're just going to go backwards. So that's where this comes in. So we went back to the previous step. And we split the 8 ohms into a 10 ohm and a 40 ohm because that's what it was originally. We combined these two to make the 8. So we're going to solve for V1, I2, and I3. Now if you remember, I said the voltage law, all these resistors are in parallel. So this is 80 volts, this is 80 volts, this is 80 volts. So we're going to solve for V1. V1 is, well, it's 80 volts because of the parallel voltages, right? It's parallel to the voltage source. Then we're going to solve for I2 using Ohm's law, which is V over R, 80 over 10, which is 8 amps. And then we're going to solve for I3, which is V over R, which is 80, this is 80 volts. So it's 80 over 40 because the resistance is 40, and you get 2 amps. Now note that I didn't simply solve for V2 yet. Well, I didn't solve for the, I didn't solve for the V here. And this is because if you remember from the previous circuit that we actually split this whatever this resistance is, as you can see 40, we actually got that from two series resistances. This is why I didn't solve for the V here, because we're going to split them into series and then solve them separately instead. Also, no, yeah, I previously said I1 equals I2 plus I3, and here you can see I1 equals I2 plus I3, I1 we solved for 10, I2 is 8, I3 was 2, and that matches out. 10 equals 8 plus 2, which is 10. So yeah, we're back to this is the previous step, and the next step, which is the complete circuit. So we just solve for V2 and V3 because we know I1, I2, I3. So V is equal to I3, V2 is equal to I3R because this is I3 and that's R. So you get 40 and you get 40 for this one as well. Now note, I didn't solve for V3 here, but I could have, and I would have gotten 80 volts. And I split it into two resistances. That's where this 40 came from, 20 and 20. And if you were to add these voltages, you would see that you get 80. So that goes with the voltage slide I said previously. The voltage of this was 80 volts. It was parallel to this, which is also 80. And if you were to add these two, it's also 80. So this is kind of like 0.1 and this is 0.2, and these two are connected, and this one are also connected, except you can simplify it to like this. Of course, these two are the same. And that's the end of this question. Now one more question. So question 2, we're going to solve for I1, I2, I3, I4, I5, I6, and voltage V1, V2, V3, V4, V5, and V6. Now I chose this kind of question specifically because, as you can see from the very beginning, well, there's more resistances, so it kind of looks more complicated, but it's the same process. But a lot of people get confused when it comes to this area. So these two are parallel. These two are also parallel. Most people can see these two are parallel. They don't really have some issue with it, but they get confused when they see these two because it doesn't exactly look like this. So I'm going to redraw this kind of, and this is going to change to this, and these two are the exact same. All I did was move this resistance down here. There's really nothing different. So, but this looks parallel, but this doesn't look parallel. So when a lot of students, well, a lot of people see this, they're like, oh, they get confused. They're like, what is this parallel series? I'm not entirely sure. Well, just draw it like this, and you can see it's easily parallel. And this just helps you visualize it. And also note, when we start from the circuit, we see I1. It leaves the voltage source, and it comes over here. It can split into three paths. One goes right, one goes up, one goes down. So what down is I2, right is I3, up is I4. You can call it whatever you want, by the way. I just called these because I just named them whatever I want. But if you wanted to, you could you could call this I3 and I2 and I4, I guess. It doesn't really matter. But as you can see, I1 is split into I2, I3, I4. So once again, that's like the 10 people analogy. So 10 people enter, let's say 3 go down here, so 4 go down here, 3 go here, 3 go here. That adds up to 10, 4 plus 3 plus 3, and that'll meet it. So I1 equals I2 plus I3 plus I4. And once the current goes here, I3 travels here. I4 also travels here. So I3 and I4 meet up, and then they split into two. I5 goes down, and I6 goes right. So I3 plus I4 equals I5 plus I6. Now question 2, so we're going to continue. So this is what our circuit is. And so we're going to start doing circuit reduction. So I combined the parallel circuits, and as you can see, 10 ohm and 10 ohm were combined, and they were 5. 8 and 8 were combined, and they were 4. So then, as you can see, the 5 and 4 here are in series, so we're just going to add them. 5 plus 4 is 9. That's where we get this. And these 9s are in parallel, so we're going to simplify that too. And we're going to get 4.5. And then these resistances are in series, so we're going to add these and we'll get 20. And this is our final circuit. So we simplified this complicated looking circuit into just this. It's the same thing. The circuit is the exact same one. And this one is much easier to solve. And we can solve for I1. Now, so we're just simply going to use Ohm's law, and we're going to get V over R, which is 100 over 20, which is 5 amps. So I1 is 5 amps. So we've solved for I1. And we're going to go backwards now. So we split our 20 ohms into 2. So we have the 15.5 and we have the 4.5. And we know I1 is equal to 5 amps. So we're going to solve for V1 and V2. V1, well, simply Ohm's law. V1 equals IR and V2 is also IR. So you get 77.5 volts and 22.5. And once again, if you add them up, V1 plus V2, it's 100 volts. Like I said previously in some slides before. So now we're going to go back we're going to go back to the circuit before we had this to this. And so we're going to solve for I2. Now, I2 is equal to V2 over R. Now there's people get a little confused here. Now, well, let's just do V2 over R. We solved for V2 before. It was 22.5. 22.5 over 9 equals 2.5 amps. Resistance is 9, that's why it's 9 here. And so we have I1 and I2. Now note, if you look at this circuit, just this one alone, which is still the exact same as this one, and the exact same as that big complicated circuit we had before, you can see that right now we only have 3 currents. We have I1, I2, and I3. I1 enters this. By the way, this is called a node. I'll go over it in future videos, but for now, let's just go with it. So I1 enters this. It's going to come here. It's going to split between I2 and I3. So I1 equals I2 plus I3 for this circuit. So if I were to use that, I1 equals I2 plus I3. So I3 is equal to I1 minus I2, just algebra. And I know I1 and I know I2. So it's 5 minus 2.5, which is 2.5 amps. Now you have to remember, this is not the actual I3 value in the very original circuit. It's just the I3 value for this. So the I3 value for this being 2.5 is not wrong. It is 100% right. But for the final circuit answer, I3 is not actually 2.5. And you'll understand when I get there, because I1 right now is only split into I2 and I3. But in reality, it's actually split into I2, I3, and I4. So I3 is not actually 2.5 in the final circuit, but in here it is. So we're going to use I3, it's 2.5, to solve for some values though, because that's not wrong here. Once again, this is just the previous one, and we're going to go to the previous step before this when we were doing circuit reduction. So as you can see, there's still just I1, I2, I3, so I3 is still 2.5, but remember, just for now it's 2.5. So we're going to solve for V3 and V5. We're just simply using Ohm's law with I3 and the resistances. So we get 12.5 volts here and 10 volts here. As you can see, 2.5 times 5 is 12.5, 2.5 times 4 is 10. Remember, I3 is still temporary, but still not wrong for this circuit. Now, this is the previous step, so next one. Now, this is where I've added the parallel resistances, sorry. So this 4 was created by these two 8s. This 5 was created by these two 10s. So we just went back to the very, very original circuit. So we're going to solve for V4, V6, I3, I4, I5, I6, all in this one step. Now remember, previously we solved for V3 and V5. V3 was 12.5 and V5 was 10. So this was V5 and this was V3 and this was V5. So V3 is still 12.5 volts. You might think that's confusing because now I3 is actually not 2.5 anymore. It's something else because we have the I4 back. But voltages in parallel are the same. And this is the exact same as these two. So whatever voltage this has is the exact same as the voltage these two have. Whatever voltage this one has is the exact same as the voltage these two have. So using that principle, we know that V3 is 12.5, so this is 12.5, and we know V4 is also 12.5, which is where we get that parallel voltage. V5 was 10 volts, so this was 10 volts, sorry, this was 10 volts, this is 10 volts, so that means this is 10 volts, they're both 10 volts. So we get 10 volts, V6 is 10 volts, so we have V4 and V6. Now we have all the voltages, we have V1, V2, V3, V4, V5, V6. And we also have all the resistances, so we can use Ohm's law to calculate for current. So I3 is V3, well, it's V3 over R. V3 is 12.5, as you can see. Remember, V3 before was 5 ohms, but now it's 10 ohms because we split it into V3, V4. So you have to make sure you do 12.5 over 10, not 12.5 over 5. That will give you the wrong answer. 12.5 over 10 is 1.25 amps, so we know I3 is 1.25 amps. And then we solve for I4, which is V4 over R. V4 is 12.5 volts. So 12.5 over 10, also 1.25 amps. So we have I3 and I4. Then we do I5 and I6. So I5 is V over R, which is simply V5 over 8, or R I guess, V5 over R, which is 10 over 8, because V5 is 10. As you previously know, we did it here. 10 volts, so 10 over 8 is 1.25, and I6 is also V6 over R, which is 10 over 8, which is 1.25. Now remember this. Now previously I said I1 equals I2 plus I3 plus I4, and I3 plus I4 equals I5 plus I6. So for I1 we got 5, and for I2, I3, I4 we got 2.5, 1.25, 1.25. Phi equals 2.5 plus 1.25 plus 1.25, and that's 5 equals 5, so that's right. I3 plus I4 equals I5 plus I6. 1.25 plus 1.25 equals 1.25 plus 1.25. Once again, that's true. Now I'd like to note something here. So as you can see, when we solved for these currents, we actually found out something. The resistances, the smaller resistances have more current traveling through them than the larger resistances. You can look at this when it comes to I2, I3, and I4. I3 and I4 have the exact same resistance, 10 and 10, and they have the exact same current, which was 1.25, 1.25. I2 has less resistance than I3 and I4. I3 and I4 have 10. I2 has 9, and I2 has more current going down to it because I2 was 2.5, I believe. Yes, 2.5. So I2 has more than I3 and I4 because it has less resistance. Now current, when it passes through a circuit, it wants to pass through the least amount of resistance. You would much rather like take the path with least resistance than more resistance. That just it makes sense. If you were to, I don't know, let's say walk through a door, would you rather walk through, and let's say if you were trying to open the door, there are people behind the door that are trying to block you. Like this is kind of a random on top of the head analogy, but let's say you're trying to open a door and there are people on the other side that are trying to make sure you can't open the door. Let's say in one path, in one door, there's one person trying to stop you. But in another door, there's like 5 people. Which one would you rather take? You'd rather take the one with one person trying to stop you, or the one where 5 people try to stop you? So that's the same with current. Current would rather go through the path that has less resistance over more resistance. So it's a good way to check your work, because if you're getting a current for a path that actually, if you're getting a larger current for a path that has larger resistance, that does not make sense, because the current does not, more current does not want to go through there. They want to go through the path with least resistance. So you have to note that when you solve, and it's a good way to check your work because it just helps you. It's not 100% like you have the right answer, but you kind of know that your answer does make sense in somewhat case. So in this video so far, we covered resistance laws, which was series and parallel law, and we talked about the current and voltage principles in a current, and we did some practice problems for circuit reduction. Hopefully this video was helpful, and yeah, thanks for watching.